Hopefully this is a right presentation. We're going to be talking a little bit about C and C++ development of applications on Linux platforms, trying to do best practice around hardening. There's a lot of material to cover, so this is a really fast overview. There's no way we can cover all the topics in any kind of depth. I'm going to try to hit the highlights of recent advancements, really, and try to give you some background on experience that we've had implementing the new tool chains. We're also going to be taking a look at some of the enhancements in the languages. It's moving so fast here as well that it's difficult for people to keep up to date. And then specifically, how do you enable some of these features on the Linux platform to improve security? So the main objectives, usually people, our clients typically want to talk about security. That's usually when we come into the picture. And we always tell them that they have to build on top of a good, solid code base first. So you need to have reliable code that works as expected. It needs to be robust to input, so you're doing all the proper input handling, post-process handling, things like that. And then finally, you can talk about security. So we're going to focus a lot on the first two here. And we're going to try to guide this through some basic principles. So we're going to be taking a look at all the tools from these basic principles. And hopefully these are fairly straightforward and standard for everyone, except possibly the first. This is relying on static verification over dynamic verification. So this is the classic argument: should I use a typeless language, or a dynamically typed language, or statically typed language? I definitely fall into the camp of try to do as much during static analysis, compile time instead of run time. And the languages that we're looking at, C and C++, definitely fall into that category. So we're going to be looking at how you enhance that capability. We'll take a look at how you default to safe behavior, so fail-safe, essentially. Least privilege. When you're writing applications, you want to make sure that you have as minimal privilege as possible, reduce your exposure to risk. Another common one is the attack surface that you're exposing. And you'll see here that Linux has put in a substantial amount of work in this area to try to reduce the attack surface of applications. Defense in depth, verification of inputs, probably everyone sees this. Defense in depth, so we're going to be showing a whole bunch of different techniques. Not any one of them is a silver bullet. We layer one on top of the other to get as much security as possible. And then another one that is often controversial for our clients is we advocate failing fast. If something goes wrong, find out and stop processing. A lot of our clients would prefer to keep muddling along, going into the land of undefined behavior. So classic example for some of our clients is they dereference null pointers all the time. Happens to work on their platform. What the hell it does, we don't know, but the applications still run. Okay, a real fast, quick tour of the new languages. And are you guys familiar with some of the newer features of these, of C and C++? Okay, so hopefully this will be new for you too. So the standards committee have released new versions of both C. It's taken a while for a new version of C to come out, so this is a big deal. And then C++ has just been cranking out new releases every year almost. So we have C11, C14, they're formally out, they're fully specified. A lot of the compilers fully implement them now, especially on the Linux platform. And many of the compilers also implement C17 to a large extent. The main goals they want to get tighter alignment between C and C++. They had diverged quite a bit in previous versions, so we got them back together. A good example of that is they now have the same basic threading model. APIs are a little bit different, but the fundamental memory model is the same between them. They've improved and tightened up the static type checking and some runtime checking as well, improving the portability, and the one major thing that everybody's been looking for a long time is native multi-thread support. So you don't have to use all these third-party threading libraries anymore. There's one standard library everybody can use across the industry. And a lot of opportunity for performance optimization, especially in the C++ world. They make dramatic changes there. So what's new in C11 first? Like I said, probably the big news is multi-thread native support now. They're using the Java memory model for the most part, with some hopefully fixes, because the Java memory model had some problems originally. That memory model is the basis of the multi-thread support. They've added Unicode support. Now, when you hear Unicode, it's not really 100%. You still have to do a lot to get multi-language support in C and C++ for that matter. But they started adding the basics of it. They have another very important feature, I think, is static assertions. We're going to be taking a look at that. You've probably all seen the assert statement. Now there's one that's evaluated at compile time, not runtime. They have a new API for replacing strings and I/O, things like that. A type-safe boundary checked with a standard error handling model. Now that's a little controversial as well, but most of the vendors look like they're going to implement that. And maybe the most surprising to the C world is they have something close to templates. They call them generics. Very limited compared to C++ templates, but it's there. And you can now overload math functions. That's why they added this, is for math. So you can do absolute on doubles and floats and complex, and they all work the same. The other thing they did, and this is the alignment with C++, is they've now made certain features that were never adopted by the C++ world as optional. Probably the biggest one is a variable length array syntax. C++ is a lot larger, so I'm going to spend a little more time here, but still go real fast. Again, they have the common set with C11, standard memory model, native multi-threading, Unicode support, and static assertions. Those all came from C11. They're exactly the same. So that's great. It makes interoperability between the two languages really nice. The one disadvantage, and maybe with the changes at Apple, Objective-C really hasn't come along with this at all. So with Apple's change in direction, it might not be important anymore. Beyond that basics, they started adding some fairly dramatic changes to language. Probably the biggest one that affects you as developers is better support for functional style programming. They have type inferencing now. If you've ever done Haskell programming or Lisp programming, where you get, even in a strongly typed language like Haskell, you rarely see a type declaration because you don't need it. That's now true in C++ as well. It changes the language quite dramatically. They have the lambda functions. So if you've done Java or, again, Lisp-based programming, you can write a function just in line instead of having to declare it first and then write an implementation in a .c file. You don't have to do that anymore. You can write little snippets of code just about any place. There's also type deduction now. So most compilers have had this facility. It's now standardized. You have a decal type. You can give it an expression, and it says, oh, that's a double, or that's an integer, or a complex function. Major improvements in the static analysis, and this will help us a lot in writing secure code. Static assertions like C11. They've fixed the broken enumerations, so you have strongly typed enumerations now. And I'm going to show you examples of a lot of these in just a minute, but I'm going to go fast through these. They have explicit conversion operators. Before, when you define a conversion operator, it got fired off whenever, implicitly. Now you can control that. They got rid of the no throw and added no except. And there's a lot of technical reasons why they did that. It's a much cleaner approach to no throw. And another thing I'm going to be advocating a lot is generalized attributes. So all compilers had a way of extending the language. So in the Microsoft world, you've probably all seen decal type. In GCC, they've had the visibility attribute. There's now standard syntax for expressing that. And they have a standard set of attributes now. And that, again, now it makes it much more portable, your code. Some usability, and what I call usability enhancements. They have much nicer initializer lists. Initialization has been standardized. There's not 10 different ways to initialize anymore. There's just one way. There's range-based loops. This is part of the type deduction, type inferencing. They got null pointer literal, so you don't have zero and not understanding what zero means. And then a whole new function declaration syntax. The library has gotten extended this way. A whole new error handling system has been added. This is true in C11 as well. In C++ is more extensive. It sits in parallel with the exceptions, so exceptions haven't gone away, but it's a standard way of communicating error codes outside of exceptions. And the primary reason it was introduced was to support multi-threaded programming and asynchronous programming, which both of those are now standard parts of the language. Smart pointers are now standard. They basically took boost library, regular expression, same thing. They took the boost library. They have hashes and tuples. Tuples have a dramatic impact, again, on the programming style. I'm not really going to get into that too much, but it's pretty cool. They have a nice random number facility, much, much better than what was there before, either in POSIX or the C++. There's optional. This is, again, if you've done Haskell kind of programming, that's a standard part of the language. Here now, if you want to return a type where you don't know if you're going to get a value, you can say it's optional. As I said, asynchronous I/O and networking go together. These last two, I think, are real winners, and we've been using asynchronous I/O quite a bit in our programs. In fact, we're converting lots of our threaded applications to asynchronous I/O. It's dramatically simpler and performs better. Performance-related changes, I'm not going to get too much into this. They have a whole new kind of reference called an R-value reference with move semantics. So when before you had the options of copying data or passing a pointer around, you now have the ability to move data, but very, very efficiently. This is going to have a very big impact on the performance characteristics of the language. They're seeing when the standard library is being updated to move semantics, they're seeing 15% performance improvements in general. Plain old data now is more broad definition. They have a more generic way of expressing constants. You can declare much more complex types of constants. They don't just have to be integers or strings. And then a way of externalizing templates for better performance. You don't get code bloat. Okay, so that's a quick tour. I'm going to show you pieces of what I just spoke about. I'm going to focus now on the language features that would be helpful for hardening your applications. And the first one is use of the static verification, preferring static verification wherever possible. So here are some guidelines that I generally recommend, and we're going to see how you can implement them in some of the new features of the language. So first, take advantage of the type checking system and use stronger types wherever possible. I'll show you a simple example of that in a minute. You can extend the type checking with generalized attributes. So the type system can say, I have a pointer of a certain type. You'll be guaranteed that they'll be pointing to that type, but you won't get other guarantees like it's not null. You can express that with generalized attributes. Static assert is a way of doing compile time assertions. Assert is runtime assertions. Remember to continue to use your const semantics, and you should consider aliasing semantics. Aliasing is a common source of both performance problems and security problems. There's a lot of difference of opinions in the C and C++ worlds. A lot of people say don't worry about the aliasing. Others say you have to be very careful about it. I'll show you some of the alternatives. So I'm going to show you a little example here. Some code and point out. Can you guys see that? So what I'm going to do is define a function that takes an unsigned and converts it to a char. I'm going to show you different ways of doing that. So the first thing I do is I have a bunch of declarations here. Char is 00 to 04. They have slightly different syntaxes, and for just pedagogical reasons, I'm passing it in by reference. So the first one is a pointer. The next one is just a reference. The char 02 is showing some new syntax and semantics. So you can now show the return type of a function after the function argument list with an arrow syntax. And they've overloaded the auto keyword, or better yet, what they've done is remove the previous semantics of auto and now assigned it new semantics. And this is one of them. It's mainly used for type deduction. So this is another way to declare 02 is exactly like 01, but with new syntax. The fourth one is a little more complicated. Here, we say auto, but we don't specify the type. The function is going to figure out the type by looking at the definition. This is auto type deduction or type inferencing. And I'll show you examples of this. And then the fourth one is an example of the new syntax for attributes. So before, you probably saw something like this. Null. That was GCC specific. Didn't work with Windows compilers for the most part. On most Unix compilers, they accepted it. But now this is standard. They have 2 square braces, scope specifier saying what domain it comes from. We're using the GNU domain. There's some standard ones that you use STD. If you were using Windows, it'd be Win, something like that. And we're saying the argument is non-null. Okay, so here's some implementations. The first one, and what I'm going to do is show you the least amount of checking to the strictest checking. Okay, so the first thing I want to do here is have a runtime check to make sure the argument isn't null. And then I also have to make sure I don't have an overflow, an integer overflow. So I use the null pointer. This is a new type. And I have, I'm just using the numerical limits library. Everyone see that? When is that evaluated? At runtime. It isn't evaluated at compile time. I then have to dereference the argument and return the result. The other thing I'm showing here is, notice the keyword auto here. I didn't have to put int char there. It figured out the type by looking at the right side of the assignment operator. So it said, oh, this type is a char. That's the type of the variable. So it's very much like Haskell, if you've used Haskell before. Here's a stricter one. What's the standard thing in C++ now? If you know you want to pass by reference, but you want to guarantee it's not null. A reference, right? The reference type, which isn't available in C, but it is in C++. I can now drop my assert. What's the advantage of doing that? Well, it's evaluated at compile time, not runtime. That's the big win. The compiler will now check for me, not the runtime and passing in a set of tests. I still have to check for a numeric overflow, though. And again, when is that evaluated? Again, at runtime. Can I evaluate that at compile time? Well, sure. Yeah, all I need to see is, before I go there, notice now I'm using another feature to determine the type of the expression. So I'm saying the type of variable result is this expression. So I'm calling, it looks like I'm calling the same function, but really that's evaluated at compile time, so the compiler can figure out, oh, this function returns a char. Okay, so there's only one point of maintenance now. Here's the alternate syntax. It's exactly the same. But here, I'm going to a static assert for evaluating the whether I'm going to get a numeric overflow or not. So you see what I'm doing is my am I going to get is char big enough to hold an unsigned? Obviously, it isn't. It's always going to fail on most platforms. But if I wanted to be able to do that, this would be one mechanism to do it. So there's a new standard operator in the language called static assert. It's defined for both C11 and C++11. And the main thing is it's evaluated at compile time. And then, and this one is the auto type deduction. So char3, I don't specify a type. Notice that I don't specify any kind of, down here, I'm not specifying decal type. The compiler figures out by evaluating the type of result, and now I have a type, the function type. So this is like templates, but a very, very simple way of expressing templates. And now let me, so I wrote a little test case. Let me actually run it, compile and run it. And the other thing I want to show you is how to actually run these things. So I'm going to use a Clang compiler. I'm going to tell it to implement the C++ 17 standard. It already supports major parts of 17. I'm turning on every single check that it can do. They have an option called everything. And the only thing I don't care about is 98 compatibility, backward compatibility, so I turned that off. And then I'm going to run the application. So the first thing to notice is I'm now going to get at compile time static assert verification. So the compile stops. I don't have to write a unit test case for that. I can that's a unit test case I don't need to worry about. The other thing is this. The other thing that I want to show is this one, comparison of a non-null pointer. I got that warning from the compiler because I annotated char04 with a non-null. And the compiler was able to do a flow analysis and said, hey, it's impossible to pass null. You never pass null in here. That assert is completely useless. Don't bother putting it in. And the compiler is helping you discover that kind of thing. Now, if I left it out, which I did on the other ones, I don't get that warning. Okay. So that's what static assertion is about, enabling the compiler, helping you find either any kind of error that you're introducing at compile time, not runtime. The other principle we're going to try to use is default to safe behavior in C++. One of the primary mechanisms for doing that is to use what's called the RAII pattern. The basic idea here is if you allocate any kind of resource, you want to make sure that by default, no matter what happens, that resource gets properly cleaned up. So with automatic variables, that happens for you or automatically. But for dynamically managed resources, that doesn't. Luckily, we have RAII with smart pointers that allow us to manage the memory and other dynamic resources automatically. And I have another simple example for you to look at there. So here are two functions, one that manages memory and another that's going to manage a file. So we're using a new library feature, something. There's a smart pointers now. One of the smart pointers is called unique PTR. There's a standard function called make unique that will do the call to new for you automatically. If it fails, it'll throw an exception, and you can then catch and do some kind of handling. However, even after the allocation happens automatically, if something bad happens, the unique pointer destructor will guarantee for you that the delete will get called for that memory automatically. You don't need to worry about it. So you don't need to clean up memory here at the end of the try, and you don't need to clean it up in the catch. It's just completely handled for you automatically. You can do this technique with any kind of resource, though, not just memory. So, memory managed languages like Java do this for you already. But what C++ has that those languages don't is a generic way of handling all resources. So a classic example is a file pointer. So say, for example, I want to use the standard fopen, fclose CAPI. Fopen dynamically allocates a file pointer. There's a whole bunch of data structures associated with that, and I have to remember to call close on it, otherwise I get a memory leak. Not a memory leak, a file descriptor leak. So what I can do is use standard unique pointer. It has an overloaded constructor where you can pass in a custom deallocator. So in this case, I'm allocating with fopen. So that's what's going to actually make make the object. And when I'm finished with it, call span fclose. And it will automatically, no matter what, an exception gets thrown, or I reach the end of the block, or whatever, wherever the scope a unique pointer, in this case the variable file, we reach the end of the scope, we're guaranteed that it gets cleaned up.
I have a quick question now. I don't use this language, the latest C++ language. So if I assign file to another variable,
Yep.
Does it keep track of that for me?
Yes, it does. So the new pointer types have ownership semantics. So if you assign one to another, you're transferring ownership to the second variable. And it's automatic. It's completely transparent to you.
Yes. If anyone has a question, ask, and I'll bring the microphone over so that your audio will go out on our live stream.
Sorry.
So let me show you an example of that. So I'm going to compile this guy. With the same kind of defaults. And you see everything passed. Now the main thing I want to show is I'm going to use the memory verification tool, Valgrind. Any of you folks use Valgrind? It's just an amazing tool. So I'm just going to run. Valgrind can do a number of different checks. The one we're going to use is a memory check, but at the same time, it will check all the file descriptors. So it can do a bunch of different kinds of resource checking. The way it works is like a little virtual machine, and it tracks every single thing. I don't have to compile the code any special way. It just runs it transparently. So I'm going to run it, and I get this report at the end. So it's saying I got 3 file descriptors at the exit, the standard in, out, and error that you would expect. So that's okay. Those aren't really leaks. It then checked my memory, and you can see nothing is lost. I do have some reachable memory, but that's okay too. There's nothing really wrong there. And notice I don't have a delete, I don't have a free. Exceptions can get thrown, doesn't matter. It's all handled automatically for you. This makes C and C++ much closer to managed languages like Java and C#, but with much better performance characteristics. Okay, let's go a little further. Another feature, and this is a feature that a lot of languages are introducing, and that's some of the concepts from functional programming. C++ is going in a major way towards this, and both the language has some native facilities for it, and the libraries are being built for it. The one I'm going to show you is the concept of a pure function. And the reason I bring it up is you should be designing your applications and libraries to have as few side effects as possible. So you define a function that does one thing and one thing only and doesn't have lots of different kinds of side effects. You can now get the compiler to check for you that you've actually implemented that contract. So the idea of a pure function, it's a function that returns a value. It's like a mathematical function. You give it an argument, it gives you a result. You don't get anything else. It doesn't modify the state of the operating system in any way. Let me shift and show you a simple example of that. And here is we're going to be using the attribute syntax of the language. So I'm going to define a function called triple, and the syntax really gets different. So I'm going to use type deduction, excuse me, the new syntax. So auto, here's a function named triple. Here's the attribute that says this function is a pure function. It's called, there's two variants in GCC, const and pure. We're going to use the const one. And here's the implementation of the function. Now notice I'm actually violating the constant rule that I just put. And we'll see what the compiler says when I do that. And the little test I have, I'm going to call triple twice with the same argument. What should happen? Let me compile it with Clang again. Okay, so compiled safe, and notice I only get it printed once. Okay, even though I called the function twice, and the reason why is I told the compiler this is a side effect free function. If you got the value of a call with the argument set to a previous value and you call it again with the same value, go ahead and optimize and use the previous value. And GCC and Clang and all the compilers will aggressively do that. So when you use const, you really need to be const. Now, unfortunately, GCC and Clang don't check for that, but we use a commercial static analysis tool called FlexLint that will actually warn you. It does a flow analysis and say, hey, there's a side effect in this function that you declared pure. And you get a compile time warning at that level. Okay, the last thing I'm going to show in the C++ world is the new error handling facility that's available. And I'm going to show you another feature of the language. It hasn't been adopted formally yet by the committee, or most of the compiler vendors have not implemented. So what I'm going to show you is the boost version of this. It's called Boost ASIO. And as I said, this whole new system error handling approach was introduced to help on multi-threaded applications. So what happens when you have two threads running simultaneously and one of them throws an exception? Who catches it and how do you handle it? Well, the rules get really complicated, and in some ways a simpler approach is to use error code, an error code approach, and that's what the C++ committee has decided as well. So here's a little example that what I'm going to do is I have a function called print, and all it does is it prints out hello world if everything went okay. And then I'm going to set up a timer that says launch call print in 5 seconds. And then while that's going on, I can do something else, like read an HTTP request and handle it, and and launch other kinds of things. So in the background, while I'm waiting for this thing to finish, I'll keep going and do other stuff. That's the basic idea behind this. I'm just showing you the one little thing that's going to print. So what I do is I create something called an I/O service. That's the magic that pieces all these simultaneous activities going on in the background asynchronously. The first thing I do is create a deadline timer. I associate it with that IO service, and I tell it what the deadline, what the timeout is. And then I tell it asynchronously wait till this occurs. And what that means is go ahead and queue this thing up and then keep going, keep executing. So it's not going to block here. This call is not going to block. So I can let me just run it first, just to show you. So I'm going to compile it. Oh, I forgot I have to link in the Boost library here. I thought I had it. Okay, it was waiting 5 seconds and it came out. So that's all you need to do. So I've set up, in a few lines of code, I've set up an asynchronous program that behind the scenes is doing a whole bunch of multi-threading. It's unbelievably simple, except you do have to worry about what if something went wrong. And the problem is I launched a program here, and how do I report back to that the handler that something went wrong? And that's and this new system error code is the mechanism for that. So you see the callback function takes a new parameter, a reference to an error code. That's the mechanism for IO service to say, hey, something went wrong. Don't just print out hello world. Try to handle it. So in this case, we're just going to print it out and keep going. You don't have to worry about coordinating exceptions or communicating an exception from one thread to another thread. All of that difficulty goes away with this. We've been using the Boost ASIO library a lot. It really is quite nice, I think. I'm looking forward to it becoming part of the C++ standard. And this aspect of it, the error handling, is very nice. Okay, how am I looking for time? I'm way over. Yeah, so let me just go real quick. I'll just mention a few things about, and this is really maybe the most important. We went over the language feature. The language is changing unbelievably fast, but the tooling is changing just as fast as well. So I've shown you Valgrind. The new compiler, Clang in particular, is just amazingly good. And GCC with an extra competition is also increasingly good too. The primary thing I would like to point you at is this here. The new tool chain have provided, I showed you Valgrind, but the new compilers, sponsored primarily by Apple and Google, have developed checkers for these tools. The ones that are most impressive are the sanitizers. They have an address sanitizer, thread, and undefined behavior. They're a little bit different than Valgrind. Valgrind is a virtual machine. It will run anything. Here you have to actually compile your code and then specially, and then execute it. It's a standalone executable at that time. But it checks an unbelievable range of errors. We combine both Valgrind and ASAN TSAN, and the undefined behavior is another very nice one. So by undefined behavior is, what if you get an integer overflow? What happens then? Right now, the thing just keeps running. With the undefined behavior sanitizer, it'll see that and report that as an error to you. And with that, I didn't get anywhere close to finishing. If you want the rest of the presentation, we'll make it available to your folks.
You still got another 15 minutes.
Oh, I do? Okay. Let me, I thought I only had an hour. Oh, I started at 12:30, yeah. Okay, let me keep going again then. Okay, so the tooling, I kind of went through that. As I said, the tooling is staying up, unlike previous versions of C and C++, where you got a standard, nobody implemented it. That's not the case anymore. Usually the compiler vendors are ahead of the standards committee, so you're getting the new standard right away. We already went through some of the annotation support, so I'm not going to go in. I will point out a few of the other ones that I haven't used so far. Some of the most important ones are the format, especially if you're doing C programming, and some of our clients have large C code bases, and we've very effectively used this. If you annotate the functions that take variable arguments, the compiler will be able to check them in compile time instead of runtime using the format attribute. The other one that's not exactly related to robustness is the visibility attribute. It has a critical impact on the overall performance of your applications. This controls, if I compile a program that has multiple .c files, library, I'm compiling a library, I only want a subset of those exported, not the full set, but there's no way of expressing that in the language. This visibility attribute goes beyond the language and says, export only these symbols, all these others are private. It reduces the surface area of your libraries. Here are some basic recommendations around these annotations. Visibility is just a must-have in any real-world applications as far as I can see. I'm surprised that a lot of open source projects still don't use this as aggressively as we really should. The annotations in general is a very simple, low-cost effort to put in that gives you lots of wins in terms of not having to write as many unit test cases. Just us putting in the non-null attribute has saved us countless hours debugging bad pointers. One thing to take maximal advantage of this is if the compiler can see more of the program as it's analyzing it, it can do more flow analysis. So I showed you a little program where it could deduce that I had a function with a non-null, and I never saw any place that it could be called without a null argument. And it can only do that if it sees all the program. I'm focused mostly on open source, but there's a very wide availability of commercial tools. Some of them very, very good. We've been using Gimple FlexLin for many years, and it has excellent support for annotations that go way beyond what GCC and Clang provide. So that would be something to take a look at. The next kind of thing is I'm going to get out of the language and get into the build process. And what do you need to do to protect your applications to the largest extent possible? And there's a surprising lot that can be done at this point. So first, and I'm going to go through a standard set of lists. Fortunately, a lot of the Linux distributions are implementing these things by policy now. It's a little uneven, and I'll show you an example of that in just a little bit. Depending on which distribution, you might want to go and check to see how good you're looking and push your distribution to adopt this. First one is the standard C and C++ libraries have a whole bunch of checks enabled internally that you can turn on or turn off. By default, they're off. You actually have to turn them on, and you do that with this fortify source and concept checks flags during the compilation process. This will look for buffer overflows, format, string misuse, a whole range of errors. So I had an interesting experience just recently where we switched from OpenSUSE 11 to 13.2. They enabled this check, and when we tried to run make on it, on a make file that has run for years, it found several buffer overflows. So we had to move up to the next release of make that I found. They've corrected all the defects. So these catch real errors in real production code that has been used like you cannot believe. Like GNU Make has had that error forever, in other words. And it only was enabled by this check. Stack overflow. So a standard attack is someone's going to get into your program, pass in like a SQL string that, or some type of input string that you're going to parse, and they're hoping to get past the stack and put their own memory there, and then jump to that and start executing their own code. That's called a stack smashing attack. There's standard tools now for protecting against that. So what they basically do is put sentinels around the stack to see if the stack has gotten compromised. All the compilers now enable that with some type of stack smashing. In the GCC and CLAN world, that's with Stack Protector option. You want to make sure that that's enabled. I got that. Oops. The next one is you want to protect yourself against buffer overflows, and this is with address space randomization. The idea here is attackers can learn the usage pattern of memory over time, and again insert some of their code that can hijack the application. So what's done by modern compilers and operating systems is randomization of the memory. You have to enable it though. Again, this should be standard when you're compiling an executable. You always want to compile with the PI option. When you're, when you're compiling a library, you always want to compile with the pick option. I'm going to go through a few more, and then we'll actually show how to evaluate the programs. The next one is when your application is starting up, how do you prevent someone from overriding one of the memory segments in the loader section? That's another common kind of attack. So this is during load up, not during normal execution. So what they've done is they placed a Trojan on your machine. They're waiting for you to start up an application. When the application starts up, they insert their code as part of the loader. You can protect yourself against that by making those loader segments read-only. You just can't write into them. It's just impossible to do. And that's with a special link option called relocation read-only. A similar kind of thing is making sure you bind to all the libraries you're going to load immediately to prevent, instead of doing a lazy loading, and that prevents someone from inserting a new version of the library and hijacking the library, in other words. So that's done with linking now instead of during the load process. You can then, these are a little bit more advanced. You can have checking, a very common error for example, the SEI secure coding guidelines warn you about integer overflows, and they have an excellent section about how different attacks that have been done by doing integer overflow. You can protect yourself to a certain degree with the compilers by enabling the strict overflow checks. So this is a runtime check. The runtime will now evaluate for any integer flow, and you'll get an error instead of muddling along and getting compromised. And same kind of thing with the aliasing. So let me show you an example of that, how you can evaluate this. I'm using the Debian distribution here, and in their last release, they went through a major effort of trying to implement a lot of these. It was pretty uneven, unfortunately, and the major problem is some of the programs simply can't be compiled with these options yet. They're not clean enough to do it. They did provide a tool called hardening check. And what you do is give it an executable. So I'm going to check how is my bash shell looking. Do I have another bash? The news last year about the bash exploit coming out. They certainly could use some help on bash. So how many of these recommendations I put were implemented? Well, they didn't do the Pi one. It's not a Pi executable, so it's a normal executable. That means it's vulnerable to that kind of attack. It is compiled with stack protection, so at least we have that part. They do have some of the fortifications enabled, and I can actually get more details on that. So you can see stir copy is protected, but fgets is not, as an example. And the last check, they have read-only relocations. That's great, but it's not immediately bound. So we can get a hijack to the C library, for example. So. Doing. Well, maybe I'll leave it to there. There's, let me just give, these are just simple guidelines for at a much higher level of compilation best practices. So you've seen some of the language, you've seen some of the compilation tools that are available. My experience is putting these in after the fact is very difficult. If not impossible, or takes many years to get in place. So retrofitting after the fact is just too hard. Try to get it in early in the development phase. Now I know most of us face legacy code bases, so this is easier said than done. And we have lots of techniques and tricks to help get this into installed code bases, but it's much harder. It's better if you can get it in. Something that's often not well understood is a lot of these checks can only be done when the compiler is actually optimizing the code. That's when the compiler is actually doing more thorough path analysis primarily to check to see, oh, there's a mismatch here, and I need to, and you only get that kind of analysis when optimization. And then you want to always check, and we've learned this from hard experience, we put in a lot of these processes and tools, and then the development staff doesn't use them. So you have to have as part of the build process a verification. So tools like this little thing that I showed you, hardening check, is a really useful thing. Okay, I'm going to just highlight a few things that I'm not going to be able to get to. If you want to, we can discuss separately. The major feature that I hope to have covered was some of the Linux kernel level capabilities or new things that are coming up. And the primary things there is, you probably all heard of containers and systems like Docker. Well, what is the technology that those are implemented on? And there's three main things that you guys should know, because you don't need to go to Docker or containers. Those are fairly heavyweight, and there's some trade-offs there. You can use all the other technologies in your programs right away now, today, without having to go to Docker. The first one is what's called namespaces. That's like change root on jails, on steroids. It's a much more complete isolation of your program to the resources that are available. The second thing are C groups. Short, it's an abbreviation for control groups. That's a better mechanism for controlling access to the resources. So you can say, that CPU can have 10% of this network. This other process can only have 30% of the memory. You have very fine granularity. The previous way of doing that was POSIX R limits, and that wasn't very complete. It missed major features. And then the last feature is what's called setcomp, something developed by the Google team for Chromium. And this is sandboxing of the kernel. So when you start up an application, a daemon, say an HTTP server, what can it do? What features of the kernel can it access? The answer now is every single feature, which is probably not what you want. They used to they had a system called capabilities to try to manage that, but that did not work out, frankly. It was too complex and wasn't useful enough. Setcomp seems to be a practical solution. You have very fine granularity. You can say, this process, I want to have only the ability to call these three system calls, like fopen, open, and close on this file, and that's it. It can't call anything else in the kernel. And you can do that on a case-by-case basis. So this is like the closest comparable thing is, the way it works, actually, maybe a better way to explain it, is in the daemon, when you start up a daemon, you usually start up as root. You release all your resources, you lock yourself into a portion of the file system, and then you call change root. And at that point, you can't get back out. You have to drop privilege at that point, and you can't get back out. But the only thing you've protected is the file system. With setcomp, you protect everything in the kernel, not just the file system. And it's a one-time thing. So you say, you start up the application as root. You say, I want to drop all these accesses to the kernel. You execute that, and you're done. You can never get them back. So the way Chrome is built, or Firefox, is what they do is have lots of little child processes that each one does only one thing. Like the PDF displayer has just one set of setcomp system calls it can make. The renderer has another, and they don't intersect at all. Okay, so that was a whirlwind tour. Any questions or comments? Okay, thanks for a comment. I had great notice.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter Longview, the new way to see what's really going on under the hood. The Longview Dashboard lets you visualize the status of all your systems, providing you with a bird's-eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.
Citrix Xenserver gives you everything you need to integrate, manage, and automate a virtual data center, all on an enterprise-class, cloud-proven virtual platform, and at 1/3 of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one-server-to-one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery, configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day. Server virtualization software separates the OS and application from the underlying server hardware. And with multiple virtual machines on a single server, you can use each of them to run different OSs and applications. This makes it possible to move your virtual machines from one piece of hardware to another whenever you want, to maximize utilization, simplify maintenance, or recover from a hardware failure, and without slowing down your applications or users. Clearly, server virtualization provides big benefits, and Citrix Xenserver provides even more. Since it's built on an open platform, Xenserver plays well with your existing hardware, storage systems, and IT management software, as well as with the industry's leading cloud service providers. Best of all, you can get started by downloading a fully functional, production-ready version of Xenserver for free. After a 10-minute installation process, you'll see how easy it is to start virtualizing your workloads and automating your IT management processes. And when you're ready for a richer set of management tools, just upgrade to one of the premium editions of Xenserver. So whether you're interested in virtualizing servers for the first time, expanding your server virtualization footprint, or moving server workloads to the cloud, download and install Xenserver today and see how it can help you simplify your IT environment. Citrix Xenserver. Do more. Don't spend more.